Hello, in this video we will discuss how particle systems are analyzed given that they are in equilibrium with their surroundings at a known temperature. So, what does this mean? What are we doing? Let us call the particles which we want to analyze lambda. Now, consider a system which contains these lambda particles. These can be created or absorbed in the system or at the boundaries through various processes. These will not matter. The important thing is that we have waited long enough for these processes to bring the distribution of lambda to equilibrium. Now, the system will have specific eigenstates for lambda, that is, states with a definite energy. Once a lambda particle is in such a state, it shall continue to be in that state in the absence of external interaction. We want to find the average number of particles of lambda in one such state given the energy of lambda in that state, the chemical potential in our apparatus, and the temperature of the system. So, how do we proceed with this? First, we need to bring the particles in thermodynamic equilibrium. Consider a mechanism for the emission and absorption of lambda. For now, let's consider an apparatus which we call gamma. Gamma can absorb or emit these particles from the state which we are considering with a change in its energy. When gamma is in its lower energy state, the ground state, that is gamma L, it can absorb a lambda particle, which gets it into an excited state of higher energy, gamma L. When gamma is in its excited state, it can emit a lambda particle and get into the ground state. Now, consider a lambda particle in this state. It has energy E. A part of this energy is the chemical potential of the particle. The rest of the energy, that is E minus mu, is the energy which the lambda delivers or carries away from gamma upon absorption or emission respectively. This means that the difference of energy between the states gamma H and gamma L is E minus mu. Now, this apparatus is brought into thermodynamic equilibrium at temperature T. This means that the ratio of the probability of gamma being in the higher energy state to that being in the lower energy state is given by the exponent of minus E minus mu divided by kBt, where kB is the Boltzmann constant. Notice that this ratio results because we have allowed the external heat bath to jiggle gamma so that it can flip between its states even without the absorption of lambda. Thus, we have brought gamma and hence the system of lambdas into thermodynamic equilibrium. Now, let's look at the emission and absorption processes in more detail. Consider n lambda particles in our state and the gamma apparatus in the excited state. After the emission, we have the gamma in the ground state and n plus 1 lambda particles in our state. Now, consider n lambda particles in our state with the gamma apparatus in the ground state. Upon absorption of a lambda particle, we have n minus 1 particles in the state and the apparatus gamma is in the excited state. Now, let's consider our state to be empty with the excited state of the apparatus gamma H. Let the probability per unit time of the emission of lambda into the state then be given by P. Can we express the probabilities of emission and absorption when the state has n particles already present in terms of this P? We can, but the values depend on the type of particle under consideration. Quantum mechanics classifies all particles as bosons and fermions. We can't get into the details of this now, but this occurs because in quantum mechanics, when identical particles are considered, processes involving them are indistinguishable, and a quantity called the amplitude of these possible processes adds instead of the probabilities of those. We have added the classical particle as a type of particle. They are identical to each other in all respects considering the problem at hand. But each of those particles are fundamentally distinguishable from each other. They shall serve as classical intuition. Now, as intuition would suggest, the probability of gamma h emitting a classical particle into the state would not change with the number of particles already present. So this probability is P. Now, if a forward process has probability P, the backward process has the same probability. With n particles in the state, there are n choices for the absorption process, and so the absorption probability is n times P. In case of bosons, the probability of emission into a state increases with the number of particles already in the state. It is given by n plus 1 times P. The absorption probability is still Np. In the case of fermions, each state can only contain one particle. So, since the probability of emission by gamma h is known to be P when the state is empty and 0 when the state has a particle, we can represent the probability as 1 minus n times P. The probability of absorption is still Np. And so we have analyzed the emission and absorption of lambda. Now, what can we say when the system is in equilibrium? We can equate the rates of emission and absorption. The rate of emission is given by the probability per unit time of gamma in the excited state emitting times the probability of gamma in the excited state. Similarly, the rate of absorption is given by the probability per unit time of gamma in the ground state absorbing a particle times the probability of gamma being in the ground state. Let n bar be the mean number of particles in our state. We can now use the thermal equilibrium and the values in the table to give us the shown expression for classical particles. It is seen to be what we would expect classically. The probability of being in a state of energy E varies as exponent of minus C upon kBT. The corresponding calculations for bosons go as shown. We see that more particles are in the state of lowest energy than in the classical case. This forms the basis of Bose-Einstein condensates. And for fermions, the calculations yield this. We see that the expectation value is always less than 1, as we would expect. And so, we have seen how to analyze collections of particles in thermodynamic equilibrium. Thank you.